Alright, so what we're going to do today is build a ramp, and we're going to roll marbles down it and such. And our main purpose is to find out what the acceleration is going to be at an angle, because we've dealt with free fall acceleration in class, we've dealt with acceleration on horizontal axis, but we haven't really dealt too much with acceleration at an angle. So what we're going to do is build a ramp, pretty much. And well, first of all, we're going to develop a theory before we do the actual experimentation to see what we think the acceleration is going to be. So we're going to start off with drawing the XY axis like this. So this is going to be our X and this is going to be our Y. Alright, and we know that this is 9.81 meters per second squared, because that's our free fall acceleration. And what we're going to do simply is resolve this vector right here to find out what the acceleration will be on the x-axis. So we could go right here, draw this arrow, and draw this arrow. So this is the y component, and this is going to be the x component. And this is going to be our right angle now. And so we have our angle over here, which is theta. That's the angle that we're going to set up. We're going to have a board and set it up, and we're going to measure this angle. And we know that this is going to be 90 minus theta, because this over here is a right angle, so 90 degrees minus theta. Alright. And so this is the new angle of our right triangle over here. So to find the x component, we're going to have to take cosine of 90 degrees minus theta, and we know that we'll call this a, because that's going to be our acceleration at the end. We'll call that a over 9.81, because cosine, as you know, is adjacent over hypotenuse. So this is our hypotenuse over here, 9.81 meters per second squared, and this is going to be the acceleration. So to find that, it's going to be 9.81 times cosine of 90 degrees minus the angle that we set up. And if you've taken pre-cal or studied trigonometry, you know that cosine of 90 degrees minus theta is simply sine theta. So this is the equation that we think is gonna help determine our acceleration. That's what acceleration is equal to.
Alright, so Ahmed already told you guys what we're gonna do. So I'm gonna put it all together, and I'm gonna put the ramp together, and we're gonna give it a go. See what happens. So I'm gonna put the shoebox here under this board to make the angle. We've already drawn a line right through the middle of this, so we're gonna put this little piece of wood here. We have marked out every 5 centimeters, so we have displacement, so we have different lines here. And we're gonna put this right in the middle, so it can guide the ball right through the middle. We know, so the ball doesn't fall off, pretty much. And then we're gonna add our little friends around here watching it. These guys are crucial. Alright, so we're gonna measure the height of this, and it's gonna be about 15 centimeters. And now we're gonna measure how long the board is. And the board is about, let's see, the board's about 85 centimeters. And now from these calculations, we're gonna get the angle of theta. And to get the angle of theta, you just put sine theta of 15 divided by 85, and that is 10.2 degrees.
Alright, and these are the 3 different balls that we're going to be using today, and we're going to find the acceleration of them while they roll down the ramp. We used 3 different balls of 3 different masses.
Alright, so as you can see, our spectators are lined up and ready to go. They're anticipating the ball roll. And so right now we're going to take these 3 balls and we're going to roll them down separately in different trials. And in the end, we're going to analyze the acceleration they go at.
Real exciting, right? Well, that's what we did for 9 different trials, and we put in slow motion just so that it would be easier to analyze and so that we could time it on the computer. But let's just watch them in fast motion now. Alright, so what we did was we took the equation that we made at the beginning of this video and we plugged in all the values, the angles, into it. And for the first angle, the 5.4 degree one, we got that the acceleration should be 0.923 meters per second squared. The 10.2 degree angle should be 1.737 meters per second squared. And for the highest angle, it should be 2.655 meters per second squared. And so we took the videos and we played them all in slow motion and we analyzed them, and what we got was that the 5.4 degree angle should got us 0.586 meters per second squared. That's what the marble rolled down at. And so what I said earlier was that from the equation we got 0.923, so not too far off. And at 10.2 degrees we got 1.258 meters per second squared for the marble, and the value that we got from the equation is 1.7. So again, it's not too far off, but it's not too close either. So what we were thinking was that maybe it had something to do with the mass, or we actually didn't take into account the friction. So that would make sense because all the values we got were slower than what the value that we thought the actual thing would be. What we found interesting was that when we did the mouse ball, we got a significantly higher number for the acceleration at 15.7 degrees, and we think that might be because of the mass. Earlier we thought that mass wouldn't have any effect, but apparently it does. So that's pretty much it. Here's a chart to show what we found. Enjoy.